Hello, travelers. Welcome to Reach the World STEM Week. For over 20 years, Reach the World has inspired youth to become curious, confident, and compassionate global citizens via virtual exchange. My name is Tim, and as part of Reach the World's efforts to support educators and families during the COVID-19 pandemic, we're using the power of Zoom to share free live stream events with members of our global community. You can find a complete listing of upcoming events, great at-home learning resources, and much more on our website at athome.reachtheworld.org. We have such a great guest and topic for today. I'm excited to welcome Professor Karen Daniels to Show and Tell. Karen is a professor of physics at North Carolina State University, and she's going to tell us about her work in physics and also what it's like to conduct physics experiments in zero gravity aboard an airplane commonly known as the Vomit Comet. To all our live stream viewers, welcome. The YouTube chat bar is the perfect way to let us know you're here and to share any questions you have for Karen today. We really want to hear from you, and we'll get to as many of your questions as possible. But without further delay, it's time for Show and Tell with Professor Karen Daniels. Welcome to Reach the World, Karen.
I am so happy to be here. And, I have to say that, Reach the World, the little slogan is bringing the world into your classrooms. And right now, most of you are not in your classrooms, you're at home. And I have to say that today I'm also going to be doing a little bit of reaching off this world, get off the surface of the world just a little bit and see what we find there. As we just heard, I'm going to tell you a bit about the Vomit Comet. That's the picture of it right there at the top. Okay, and the reason that we were riding the Vomit Comet was we wanted to learn how to explore asteroids. So let me tell you a little bit about an asteroid I like named Bennu. And Bennu is super cute, right? Bennu is only 3 football fields across in diameter. And in fact, behind me is a picture of the surface of Bennu. And these pictures were all taken during a NASA mission called OSIRIS-REx that is there now. And actually we'll do a sample return. And so in 3 years, we'll get to see pieces of this. And this is a movie composed of static images assembled to make it, you can tell it's spinning. And you can really see what it looks like. There's light from the sun that gives it shadows. And it's not round. It's kind of looks like 2 pyramids almost stuck on top of each other. So it's a strange object. And one of the cool things about little cute asteroids like this is that they have very little gravity. And that's, and gravity, of course, is the force that attracts one mass to another. Okay, and so we're familiar with this on Earth quite from a lot of daily experience. Okay, and so 1g is the amount of gravity we feel standing on the Earth. And if you were to stand on the surface of Bennu, you would feel 6 micro-g's. And that's what, and so microgravities. Okay, and micro here means 1/1,000,000th. Okay, so this is tiny, tiny little bit of gravity. And so I want you guys to all think about what might happen if you were to be standing on Bennu, okay, or if you were a robot standing on Bennu, and you were to pick up a rock and throw it, what you think might happen. So I'll give you guys a second to think about that, and you can type some of your answers into the chat bar, and then I'll get a chance to hear what your ideas.
Absolutely, yeah, please. If you have an answer to Karen's question, what would happen if you threw a rock? If you're standing on Bennu and threw a rock, what do you think would happen? Add them to the chat bar and we'll share them with Karen.
So if I were on Earth and I would pick it up and throw it, it would go a little bit forward and then it would land at my feet in front of me. Okay, but remember the gravity is 1/1,000,000th here. So I don't have a very strong arm. How would I do?
All right, well, let's see here. Let's see if we have any guesses. Drop your guesses into the chat bar if you have one. Karen, why don't we keep going? Maybe you can tell us.
Keep going, and people can think about this. And I'll tell you what I think would happen.
Oh wait, hold on. Sorry, we have a guess. We have a guess. Lucas is guessing that it would take a while to fall. Would the rock go up and take a long time to fall down again, or maybe it wouldn't fall?
Exactly. You've got it exactly right. It would take a long time to fall. And so if I throw it forward and it takes a long time to fall, right, it's going to fall forward and it's going to go a long way. And what does that look like? That starts to look like an orbit, right? So in fact, it's very, very easy to throw a rock and put it into orbit on an asteroid this small, okay? And you guys may have heard of escape velocity, which is how fast you have to throw something to have it leave and never come back, right? And on Bennu, that escape velocity would just be a few inches per second, about how fast a feather falls, right? So even though I'm a terrible pitcher, I'd be able to throw things at escape velocity on this object, which is kind of cool and makes it a little weird. So you've probably noticed something else about it. It looks like Bennu is made of rocks to us, right? And you can see pictures right here. And we know from Earth that rocks have, say, about 3 times the density of water. Some are more, like, 5 or 6, some are a little bit less, but let's use 3, okay? And using measurements done, about Bennu, we know that it has a density about just 1.25 times that of water, okay? So how is that possible, right? If Bennu is made of rocks, how is it? So one possibility is that the rocks are less dense there, right? So you could have fluffy rocks, maybe. Okay, and we actually see that in volcanoes on Earth. That's possible. And the other idea is that maybe the rocks look a lot like, grains that we have in our kitchen. And if you look at the grains inside your kitchen, this is some bulgur. Right? There's a lot of space between them, right? Okay, so maybe they're just not packed very tight together. So on the whole, only about half of it is taken up by rock and half is taken up by empty space. So it comes out being kind of fluffy. Okay, and that's the reason that this kind of asteroid is called a rubble pile asteroid, because it kind of just is a loose pile of rocks. Okay, and do you guys have any idea what might hold Bennu together? Because it looks like a solid object, right? We see it rotating like a solid object. So any ideas what holds it together? It's not chewing gum.
Oh, sorry there, I muted myself for a second. That's
Right.
such a good question. We learned that there's not a lot of gravity, so it's got to be something else, right?
Well, I don't know. So here's the thing: does gravity still work in space? It does, right? So even these little rocks have a little bit of gravity pushing them together, right? So there's a little bit of gravity still. Okay, so we know that's still there. Okay, because that's everywhere. As far as we know, that covers the entire universe. This is one of these laws of physics that we think is everywhere. Okay, so we think there's still we're pretty sure there's still gravity holding it together. Okay, it's possible that there's little bits of sticky molecules, right? And so on Earth, you may have had the experience that when it's really humid out, just a little bit of water can stick things together. Okay, well, there probably isn't, that isn't happening where it's very cold in space, okay? But there might be just little bits of sticky adhesion between materials like, so things called asphaltanes, okay? So basically other liquids, okay, might still have residual amounts, okay? And these are called van der Waals forces sometimes, right? The little chemical bond, we are very, very weak chemical bonds might be enough to hold it together, okay? But yeah, it's just probably very, very delicately held together, okay? It's a very, very weak object. It's not like jumping into a pile of sand on the Earth where you would probably say, ouch. Okay, so this brings us to a question, right? So are these things we're talking about, like sand, are they solids or liquids, right? So I'm showing a bit of a little video of an hourglass on the left, and you can probably see, and I'll play it one more time for you guys. You can probably see there's like a stream of sand falling down. That looks a lot like water. Okay, it's behaving like a liquid. Okay, and in fact, you saw that when I showed you guys the bulgur too, right? We've got, it flows a bit, doesn't flow exactly like water, right? So an example is I can tilt this and here you go, a little bit of weird reflections, but you can see that it comes to an angle, okay? And that seems to be true of most grains. I've taken a couple other ones here. Here's some lentils, it's the same thing. It makes this angle right here, okay? Which we call the angle of repose. And there's a photo I put on of some piles of salt that I saw when I was visiting the island of Bonaire in the Caribbean, and they get these beautiful straight lines. This is not what a water droplet looks like, right? A water droplet would keep flowing down until this was all flat, okay? So sand is a bit like a liquid, okay? It can flow, okay, but it's a bit like a solid. You can still walk on it, okay? I think many of you who may have been to a beach or played in a sandbox probably, have had that experience. It can go back and forth between the two, okay? And it doesn't go back and forth. You have to, if you push on it or you poke it, right, or you leave it next to an open hole, like it'll switch its behavior. Okay, and as a physicist, I find that super interesting, and that's one of the things that my lab studies is how does this material know how to go back and forth between these two behaviors. Okay. But in this context, there's a really important application to that knowledge, right? Is that if we're going to visit an asteroid and either humans or robots are going to explore it, right? We have two really important challenges that NASA has to think about. And one is you don't want to make a mess of the asteroid, right? I told you guys the escape velocity is a few inches per second. So if you start digging and shoveling on there, you could easily break up your whole asteroid, right? Okay, that's a horrible mess. It's dangerous for you. And one of the campsite rules, if you go camping, is don't leave a campsite messier than you found it, right? And so we need to make this rule when we go out exploring the universe. So that's a challenge. We could easily make a big mess of the asteroid. And while we're making a big mess of the asteroid, we might accidentally make a big mess of the human or the robot exploring it, which would also be terrible. Okay, so this is where I got my brain thinking about how might we deal with these issues. Okay, and I got to thinking about something I see, around my life, which is that, if you were to go, let me just back up a slide here, right? If I were to go and try to harpoon this thing and fire something into it, right? I might make a giant mess, right? But is there a way I can sneak in and be quiet about it so I don't make a mess of the asteroid? And I thought about plants, right? So plants send entire root systems down into the ground, right? And they are able to do that without disturbing any of the grains by very much. Everybody just moves a little bit. And I took these pictures out of a recent PhD thesis from a scientist whose work I follow, because he took these wonderful images of roots growing inside, and he used clear sand here, so like glass beads, so that he could see what they were doing. And all those roots have wiggled their way in, so they didn't move the dirt someplace else. Okay, and so this is something that engineers sometimes call bioinspired design, right? So we've seen some organism on Earth do something clever. Can we use that when we design something new, right? So this, in the context of asteroids, that comes to ask the question, is it better to approach the asteroid slow and gentle or fast and powerful, right? And you think of NASA and rockets, and your immediate go-to is to be fast and powerful. And our idea was maybe we should just calm down, take it slow and see what happens, okay? So that was our experiment. We decided we wanted to do an experiment to see if slow, gentle digging was a way to not disturb all of the grains on Bennu. But of course, we can't go to Bennu, right? NASA already sent its mission, didn't send any people. I forgot to hitch a ride, okay? And so we got to thinking, let's ask NASA if we could have a project to try this out on Earth. And to do that, we were gonna try to get microgravity on Earth, okay? And this became a project. And the folks you're seeing here are a project we called Empanada, which is an acronym that stands for Ejecta Minimizing Protocols for Applications Needing Anchoring or Digging on Asteroids. So in other words, ejecta are the stuff that comes flying off the surface, and we don't want that because that's the stuff that's making a mess, okay? And so this is the team of folks we assembled. So these four folks here were all at the time physics and engineering majors at my university, North Carolina State University. So Robert, Anna, Tristan, and Riley. And then the person at the end here, that's me, and is Jonathan Kolmer, who is a scientist from Germany who had prior experience building experiments to go into microgravity. So the four students designed and built an entire apparatus, and you're seeing them working on it here. And we went and did experiments that would help us test this idea that something slow and gentle was a really good way to sneak an object that could either anchor or dig on an asteroid. So now I'm going to tell you a little bit about what that process looked like. Okay, so how did we turn off gravity? Well, you can't turn off gravity because it's everywhere in the universe. All masses attract each other. But there's a trick, and you may have had this happen. So I'm going to ask you guys a question, and you can, if you don't want to chat about it, you can just chat with whoever you're in the room with. But how does it feel when you're in an elevator and it starts going down? So I'll give everyone a chance to think about that. And if you have some ideas, type them.
Karen, I'll share any responses with you as they come in on the chat.
Excellent. So I've had the feeling sometimes if I'm standing in an elevator and it starts to go down, it feels like the bottom's dropped out from under me. This is like this person is someone who, unfortunately, the cable has seems to have snapped on his elevator. Okay, but we've all seen amusement park rides where you do this too, where you take something up to the top of a tower and they let it go and you fall down. So that would be a great way to get microgravity, right? Because it feels like you're just a bit lifted off the floor, right? And in fact, this is something you guys can try at home. If you live in a building with an elevator, ask your parents if you can borrow the bathroom scale and go ride up and down in the elevator, standing on your bathroom scale. And what you'll notice is that when the elevator just starts to go down, it looks like you weigh less, okay? And when the elevator starts to slow down, you're still going down, the elevator pushes up into you and you start to feel a bit heavier, you push more on the scale, okay? So we can't turn off gravity, okay, but we can make it so that we are for a little while feeling its effects less. Okay, and now your stomachs are very good detectors of this, and this is why it's called the vomit comet, right? Is that that uneasiness you feel in your stomach is that your stomach is used to not moving relative to the rest of your organs, and when it does start doing that, your brain says something's up.
Karen, we have a couple people on the live stream who have correctly guessed, who understand the feeling that you're describing, where you feel less gravity as you're coming down in an elevator. It's a great example.
Yeah, so yeah, those of you who didn't ever experience that, now pay attention the next time you're in an elevator. The other place you might feel it is exactly what the vomit comet does, okay, which is it flies straight for a while as if it were a regular flight, and then it goes into a steep climb, and then it goes over the top of an imaginary bump. And some of you may have had the feeling in a car, sometimes your car goes over a bump and the same things happen. And again, your stomach feels like it's lifted up. Okay. So that is that same reduced gravity feeling. And so a vomit comet is just a plane, and ours was flown by the companies called Zero G, where they fly you in an up and down pattern. You can see all the zigs and zags. This is our actual flight path that I downloaded. Okay, we had real airline tickets. We took off and landed from the same airport. Okay, we climbed up to regular cruising altitude. It's just that we zigzagged up and down like this picture down here. And every time we went over the top of the imaginary bump and the pilots were steering it over the top, we would feel a period of lower gravity. And we did stuff that was sort of fake Martian gravity, so like a third of the Earth's gravity, lunar gravity. Okay, so fake lunar gravity, like on the moon, and that's like a sixth of the Earth's gravity. And then zero wasn't really zero. It was about 1/1000th of gravity, which was small, but not as small as Empanadas, which we said was 1/1,000,000th. And so we did a bunch of these, you can see. We zigzagged up and down, okay, and then we flew home. Okay, and so that was where we did our experiments, every time the pilots took it over the top. Okay, so I will show you now. So here's what that looks like. We had to go there and use this lift to load our experiment into the plane, okay? And then once it was all bolted down, we could do all of our tests to make sure everything was working. This is me posing next to it. And I'll show you a bit about what the experiments are next that we actually did using this cool apparatus, which is basically a robot. Okay, so the Empanada team basically built a robot that pokes, okay? And for you to understand the data, I have to do a little bit of explaining what this looks like. Okay, so the first thing is we had to learn how to do stuff in zero gravity. And the only way to learn to do it is by going up and trying it. So this was our very first zero gravity. Okay, so I'm gonna play it. And what you're gonna see is we're gonna all be on the floor when it starts. And the pilot's gonna call out that we're about to go over the bump. And so we all sit up and get ready to run the experiments. Okay, and then you'll see how well we do at running the experiments. All we were supposed to do is push a button. Just walk up to the experiment and push the button to start. That was our goal. Whoops. Whoops, I went back. Let me try this again. Here we go. This might take a second to load. All right, so we just got the call to get up and push the button and check how the experiments are doing. Right, and now we push the button. And what happened to us? So that's Robert, and then me, who went off in the wrong direction. Okay, so we were beginners, and we forgot that we were physicists, right? And one of the physics laws is that if you're in motion, you're going to stay going in the same direction at the same speed unless a force acts on you. And so if we pushed off by pushing a button and got some speed, there was nothing to stop us, nothing to change our direction. So we just kept traveling until we were in danger of hitting the other poor people doing their experiments, right? Which they maybe didn't want us to be doing, okay? Which is why this is actually one of the directors of the company. She pushed us back. She was experienced. So we did better the next time. We didn't accidentally push off the experiments. So let me play that again. So if you didn't catch how we messed up, you'll have a chance to see it. Okay, and it's fine. We did get data, and we got better at not screwing up after the first run. And you'll see us. But unless we push off of something, we can't change our direction. And that was really tough to do. The other thing they warned us about is to not swim, right? And so you'll see that we're waving our arms around, right? And they warned us not to do that, because the closest feeling we have to this is like when you're in a swimming pool and you're floating. And if you want to move, then you move your hands and you move in response, right? And you go back, right? But that's because you have lots and lots of water to push off of, right? That resists it. When it's just air, it doesn't take much resistance. There's not much to push off of. And so we were very, very poor at swimming in air, right? And so we tried and we failed. Okay. So that was, we got better at doing our experiments after the first 1 or 2 tries. Okay. And now I'll tell you a little bit about what those experiments were. So what we want to be able to see is how hard we're pushing on the materials. Okay. And to do that, we make what we call spy grains. Right, so these are a special kind of plastic that does a light trick, so that the more you squish on them, okay, the more force that's on them, the brighter they get. And I'm going to show you this live with a little demo here. Well, it's live for me. It's unfortunately not live for you. All right, so I'm going to go stop share for a second so that you guys see me nice and big. Okay, so here's just a light screen. Okay. And I'm going to put some of these particles in a box in front of you. And what you can see is that I push on them, they get brighter, right? And if I don't push on them, they get dimmer. So this can tell me, and real sand doesn't make this so easy to do, but this is plastic sand with a nice light trick. So I can spy inside and see how much force and where the force is inside an object. So that was sort of a mini version of the experiments that we actually did on the vomit comet. Okay, so I'm going to show you some movies of that. Okay, and these should start again in a second. And the one on the left was done when we were going over the hump like it were Martian gravity. And the one on the right is the one we were done when we were going on like we were on the surface of an asteroid. And so this is us digging into a pretend surface of a rubble pile asteroid with these magic spy grains that let us see what's going on. So the one in the Martian one, the digger hits and it keeps getting stuck on grains of sand, okay? And it pushes on them and then it eventually figures out a way around it, right? I think this is something like the teamwork that we had in our group. We kept getting stuck when we were designing the project and getting under pressure and having to figure out a way around it and having to be flexible, right? So a flexible probe meant that we never got any giant disturbances, okay? And the one on the right, which is in microgravity, right? And that one's running a little bit slowly. I apologize. This is not the best movie to play over a live stream. It's not even making any of those forces show up, basically, right? So it's able to completely sneak through. Nobody gets under any pressure, right? None of the grains feel squished. It just gently weaves its way through. Okay. So what we learned from this, and now what you see is we're about to have gravity going the wrong direction on the right. The grains start going up. And so this was something that was a problem the day we had the flight. We encountered air turbulence, which meant the plane was getting jostled around. And so we had sometimes when gravity went the direction we didn't mean it to do. Okay, and this was one of those runs. So what we learned from this was that having a flexible digger is a really nice strategy. It lets you not disturb grains. They don't go flying up, okay? And it works maybe both on missions to Mars, which is the one on the left, and maybe on ones that eventually go to asteroids as well. Okay, so we were super happy. This is Anne and I looking very happy that we had collected data and we had not thrown up. And we were walking back from our flights to download the experimental data, bring these samples back to the lab, and start the process of analyzing the data, which is what we have been doing since we took the flights. And at this point, I'd be happy to take any questions you guys have. You can type them in the live chat, and so that I can answer them. I think you're muted still.
Sorry about that. Thank you, Karen. That was amazing, and you're so good at explaining that in terms that non-physicists can really understand. That was really great. And right at the end, you answered what is probably our most burning question. I know it's already been asked in the chat. Did you personally vomit on the vomit comet? Or
So I did not personally vomit, and I am proud of that. But I have to say I did take Dramamine. So I took motion control pills, and I felt fine the entire time. So what they told us was usually about 10% of the people throw up, and that was our experience. About 10% of the researchers had to leave their experiments and go back into the plane seats. There actually are plane seats on the plane, and they had to go buckle themselves back in and have their air sickness bag. And I'm told that it's not a trivial experiment to keep the vomit inside the air sickness bag. So the sick scientists are still back there doing experiments, unfortunately, as they get sick.
Oh,
but
no.
It happens to everybody some of the time, I'm told. Even people who are like, I've done this 100 times, they might go one day and they're just off. And so it's not a matter of being stronger or weaker. Just, our bodies aren't used to this, and sometimes you throw up.
Yeah, are there any other ways besides the vomit comet to replicate these low gravity or zero gravity situations for physicists like yourself, or is this really the primary way to do that?
There are other ways. So we picked this one because we could get 20 seconds of experiment each time, and 20 seconds was just enough for do one of our experiments. And so it worked out really well for us. But there's two other really nice ways to do it. So sometimes people will get their experiments launched onto a long rocket trip. And so the rocket goes up for a while and eventually comes down. And that gives them a nice long stretch of microgravity. They still have air turbulence, right? So that's also a problem. And you also can't be there sort of troubleshooting the experiment as you're doing it. It has to be completely automatic, but that's another way that lots of experiments get run. Another one is what's called a drop tower. And that essentially is the elevator amusement park experiment I described. So space agencies will build a tall tower, okay? And actually they do something more clever than just drop it. They actually started at the bottom and they launch it up and down so it gets twice as much time, okay? Unfortunately, that's only a few seconds, okay? So that's really good if you only want a few seconds of data. And the nice thing there is in between, you never have to feel sick. You just sit there and fix your experiment and launch it again, right? So that's actually a really nice one. And then the coolest one is that you get to send your experiment up to the space station. And then it can stay there for many months doing lots and lots of experiments, right? And then the astronauts are actually the ones who do the experiments for you, not you. But it's still a person who gets to do them. And this is why many of the astronauts are trained scientists, is they're up there doing people's experiments on the International Space Station.
Okay, very cool. We have another great question from Lucas in the chat. He wants to know, how far have you gotten in your project and what are your next steps? Is this something that you hope to send to the International Space Station someday?
So yeah, so one of the goals of this project is to learn how to do this experiment in microgravity. And so actually some of our experiments worked and some didn't, right? And that's actually pretty normal for experiments, right? They're called experiments for a reason, right? You're not really certain how things are going to turn out. So the status of our project is that enough of our experiments worked that we can publish some papers that describe what we saw, okay? And now we are more confident that we could design a better experiment, right? That would get better data and be more detailed and better numbers and cleaner and all of that. Because we've got practice, we're getting better. So the next step for scientists is usually to go and try to plan a slightly more complicated experiment and see how that goes, right? And then if that goes well, you try to do something even more complicated. So it would be great to one day fly something like this on the International Space Station, right? But I just described to you a bunch of experiments we can do on Earth, right? And so this is a question as a scientist is, which of these platforms do I pick right? They all have pros and cons. It's super cool to get to do a vomit comet, but we only got 20 parabolas one day, 20 parabolas the next day. It's only 40 data points, right? And so that's a little sad, right? But we got to do the experiments ourselves, which is nice, right? Some of the other platforms have pros and cons, like I have to send it off and hope it works, right? And so you need to be a lot more confident that you know your experiment is a solid experiment before you go off and try to do one of those sort of higher risk ones. So I would love one day to fly an experiment on the International Space Station. That would be just a marvelous, marvelous experience.
Great, thank you. I know we have a lot of students on the call today who are hearing what you're saying and thinking your job sounds really, really cool. How do you become what you are? Or how did you become, and what would you suggest for kids who want to be physicists and do work like this?
So, I mean, a physicist is anybody who likes to ask questions about these ideas. How does matter interact with each other? What are the forces involved, right? And, you know, you guys can be physicists now, right? You know, you can ask questions, you know, like I just showed you some stuff from my kitchen, right? So like, did you notice that things that are, you know, I can make really high angles for some types of grains in my kitchen. And, you know, for other kinds, it's a lot harder to make high angles, right? So you can start doing experiments now. And those are the kinds of skills that scientists need to like get good at being scientists, right? They're things you start whenever you feel like starting them. So the things that let you become a professional physicist, right? Anybody can be a physicist, fair square. It doesn't matter how old you are, how much you know. Okay. But to be a professional physicist where they pay you to do it, there's a thing you have to know, which is math. Because in fact, the language we describe all this in is math. So how fast is something going? What direction is it going? Is it speeding up? Is it slowing down? Right. And so the best thing that a student can do to prepare to become a physicist or an engineer, and you know, a lot of the students who worked on this project are hoping to go work in aeronautics and aerospace industries, right? They all took lots of good math classes in middle school and high school, so that when they got to college, they were prepared to take the cool physics and engineering classes. So those are the two things that you guys can do right now. Is, you know, start practicing running experiments just of your own, writing little computer programs on your own, doing good math problems, so that your brain is all nice and worked out. But there are also students who get to college and then suddenly decide they want to be a physicist, and they start it when they get to college. And I know people like that too, right? So there's lots of paths. And the students who worked on this project, you know, one of them is off getting a graduate degree so that he can learn to run space programs. Another student is working on launching satellites that monitor our atmosphere, right? And so these are all different flavors of being people who love this material, right? We're all doing kind of different stuff, right, with it.
Very cool. You are, Karen, a member of our global community, and through your work and your personal life, it looks like you get to do some really cool things, including go to places like Bonaire and ride the Vomit Comet. And I want to finish our talk today with a question we pose to as many of our people we speak to as possible. After you are released from your COVID-19 home, wherever you're sheltering, what's the next adventure or place you'd like to go?
Oh my goodness. So I have become, in recent years, very, very fond of volcanoes. And so as you notice, so those pictures of Bonaire, of the salt cones, those were just a holiday picture. You know, when often on holiday, my brain is still looking around at, you know, the water and the waves and the rocks. And I am absolutely loving volcanoes these days for a couple of reasons. They have all these cool fluid flow problems, right? Where things are between solids and liquids. They make wonderful swirly patterns in the lava, or chunky patterns with fractures in the lava. And so one of my next trips when I get unlocked, I hope, is to go someplace where there's cool volcanoes. They're just amazing.
Awesome. That sounds like a great trip. And unfortunately, that brings us right up to our limit of time that we have for today. I want to thank you so much, Karen, for joining us and
Thanks so much for
your
having me.
experiences.
And I'll go read all the chat questions when I get off.
Yeah, please do. And thanks to our entire YouTube live stream audience for joining us today. Tomorrow is our final day of STEM-focused live stream events at Reach the World. We're going to spend it tracking animals on an island in the middle of the Panama Canal and simulating a journey to Mars. So lots of exciting things left to go this week. I hope all of you will join us, invite your friends, and you can check out the complete calendar of events at athome.reachtheworld.org. So we'll see you next time. Thanks again, Karen.
All right, thanks so much.